Okay, so this is for the physics periodic, term 2, week 4. These are the past papers I'm going to be solving over here. Okay. Um, Again, sorry for the mic, but I'm not in the country for whatever. Okay, the first past paper, it's the label on the top left. Figure 7.1 shows a coil of a wire wound on a thin plastic cylinder. So this is the over here. Enable editing. Okay, this is the coil over here on a plastic cylinder. The plastic has no effect on any magnetic field, and there's a galvanometer wrapped around it that's extremely sensitive. A magnet is fixed to a small trolley that runs without friction on a track through the cylinder and coil. The trolley is released from point A, so it runs through the coil from right to left. So it goes like this, right? State and explain what is observed on the galvanometer. Obviously, since you have a current, you have no, not a current, you have the magnet over here, right? It's inducing when it comes to the left, it's going to create a magnetic field, right? It's going to have this magnetic field. So you have this B, you have the force. Why is there a force? Because the trolley is moving. Remember, F, B, I. What does the galvanometer measure? You guys know galvanometer measures small currents, right? So this small currents, basically we're talking about the I. So you have this B, you have the force of it being pushed in, right? You have the magnet being pushed into a coil. What happens? You get a deflection on the galvanometer. So what is observed? It's a deflection. And let's see what are the points on the marking scheme. I don't want to make anything up. Hold up. It's over here. They said deflection. These points are all correct, but this, if I were to choose one, I would choose this one. Change in the magnetic flux. Remember, having an induced current, it was Faraday's law. Induced currents are formed due to the change in magnetic flux. So this small current detected by the galvanometer, why do we see it? It's a deflection due to the change in magnetic flux. We'll just call it phi. Okay. The trolley is now released from point B. Where's point B? Over here. So it runs through the coil from right to left again. State what is observed on the galvanometer and explain why it is different to your answer in AI. Obviously, let's erase this just so you can see a bit better. They said أخذوا الtrolley now, they took it, they put it over here. So you have your trolley now over here, it's at a greater distance, south-north, and they released it, it went down, right? So here's the thing, what's going to happen now? Obviously, there's going to be, let me change my color. Obviously, there's going to be a larger deflection. Why is there going to be a larger deflection? Because it's going to obviously, wait, larger deflection. In the marking scheme, they said because it's moving at a higher speed, or you can just say, like we said in part A, because there's a higher change in magnetic flux, right? This is magnetic flux. Remember, we always say, how do you affect the change in magnetic flux? To affect the change in magnetic flux, you can move the magnet at a higher speed. Moving the magnet at a higher speed causes a higher change in magnetic flux. And you guys know a higher change in magnetic flux causes the induced current. So since you're moving faster now, there's going to be a higher change in magnetic flux, which will cause a larger deflection. Okay. Figure 7.2 shows an extension lead used to supply power to a 3 kilowatt heater on a cool evening. Okay, so here we have the heater over here. You have damp grass. Damp grass, by the way, kind of it means like wet. Okay, and then they have a cut in the insulation, which obviously is a problem. And then we have a plug and a socket lying on grass, which I guess is an extension LED designed for use with a 25-watt lamp. And over here you have a paved area. State and explain 3 dangers with this arrangement. Obviously, they're telling you 3 dangers, and they gave you 1, 2, 3, 4, 5, 6. So I don't think there's 6 possible answers, but I'm pretty sure you can get 3 very easily. And from what I can see right now, is the extension lead designed for use with a 25-watt lamp, but this is 3 kilowatts. So obviously the first thing I'm gonna see is this is wrong, right? The second thing I'm seeing is the cut in the wire. if it is a cut in a wire and it's wet grass, then I would presume as well that it's going to leak electricity and it's going to cause short circuiting, because when water leaks into an electric circuit, you guys know it causes short circuiting. And I think here paved area, I think that's something else. Let's check the marking scheme. Also, I don't want to say random things. Okay, so the current uh, slash power is too high or trip hazard, and cut. Oh. Okay, yeah, so the short circuit was correct. Uh, the short circuit because of the wet grass. Okay, yeah. Okay, yeah, yeah. So these count as two actually. The wet grass causes a short circuit because obviously, yeah, I don't know if you guys have tried before, but if you guys have like a circuit or a plug, those the plugs where you plug in your chargers, if you put in water into it, the whole house's electricity actually turns off because it short circuits it. So water doesn't work well with electricity, so it's going to short circuit due to the wet grass. It's also going to short circuit because the wire is cut, so that's two. You could say overheat. I wouldn't say overheating. uh, Trip hazard. Okay, trip hazard is good because what they mean by trip hazard is you're probably gonna trip. Look here, it's on the grass over here, so someone running can go like woo and you'll fall down. So yeah, trip hazard is actually a good one. So we can say, I'd say trip hazard. So I just understood the overheating one because I was seeing it. I was saying like, what's why? It turns out overheating is because the power required is too much. Because remember we said over here, just over here it's 25 watts, but here it's 3 kilowatts. So it's designed to only give 25 watts. So obviously, I don't know how I didn't think of this. It's gonna give too much power, but it's only designed to give 25 watts. You guys know the more power you give, it's gonna overheat, and then this wire will melt. So you can just say we'll start one by one. We'll say overheating of the wire, right? Overheating of wire because uh, power power required is too high. Then we're gonna talk about, you can say tripping, I guess, Wasani. This is if you know this, it shows you kind of understand the concept of what we're taking. The second danger, obviously, electrocution, or you could say short circuiting. So electrocution, most people know what electrocution is. Short circuit is a word not many people understand. Short circuit basically means the electricity turns off. Electrocution because wire is cut or insulator is cut, right? And we could say electrocution from the water or wet grass, right? Wet grass. So this is easy and it gets you an easy 4 marks. If you were just to say these three without explaining, like for example, the first one you had to say the power has to be too high. The second one, it's just cut, so you can't really explain it. But this first one, if you just said overheating, بيطلع لك 1 mark, just 1 mark, and that way you're only going to get 3 marks. But it's a 4-mark question. So the 4th mark you would get from saying that, explaining the first one, why would it overheat? Why? Right? You need to say the power is too high. I know for the people who aren't doing IGCSE, they see this, they say, no, like, this guy's talking too much. But really, it's very important for those who are doing IGs because you're going to lose marks al-fadhi. And the school will follow the IGCSE marking scheme when correcting your paper. Okay, new paper, October, November 2018. Obviously, paper 4.2. This figure 9.1 shows a permanent bar magnet next to a circuit that contains a coil and a galvanometer. Same as the last question, almost same arrangement. Suggest the metal from which the magnet is made. You can say any one of the ferromagnetic materials, either steel, nickel, or cobalt. I'm going to show you the marking scheme. It's just steel, nickel, or cobalt. I won't switch tabs. Because those are the magnetic materials. The magnet is moved to the left and inserted a small distance into the coil. The galvanometer deflects briefly and shows that there is a current in the coil. Explain why is there a current in the coil? FBI. When you take this magnet and start inserting it, there's going to be a change in magnetic flux, which causes an induced current. Let's see the marking scheme. Part B, change in magnetic flux. and induced current, right? Or you could say induced EMF. You know what? It's easier, actually, it's nicer to say induced EMF, okay? Uh, because some people, some boards, some academic boards, they don't recognize induced current. They call it induced EMF. Our school calls it induced current, and sometimes calls it induced EMF. So just say induced EMF, okay? Let's switch back. So you can say there's change in magnetic flux that causes an induced EMF or induced current. But in our school, they would probably accept induced current. As a magnet is moving near to the coil, end Q of the coil behaves as a magnetic pole over here, right? State the polarity of end Q and explain why it has this polarity. So many people see this, they're going to be very confused. But there are two things you have to remember, the two laws that we spoke about in this inserting the coil وما بعرف شو. But inserting the magnet into a coil, we have two laws that we're working with. The first one being Faraday's law, which states that when you do this switching and inserting or شو, there's going to be a change in magnetic flux that causes induced current. Then the second law was Lenz's law. Lenz's law said that, okay, you get this induced current, but it's always going to oppose the motion. Remember what I told you, Lenz's law? Lenz's law is always that ungrateful neighbor. So whenever you push this magnet inside, it's going to repel you out. And when you're coming out, it's going to push you back in. Okay? So now they said that the magnet is moving near to the coil. So enter, you're going inside here. Okay? They're saying that this point Q behaves as a magnet. What is its pole? What pole would it behave as? Remember, it always does the opposite. So if you're going inside, it pushes you outside. Okay? For it to push it outside, obviously Q will have to behave as a north pole, because north will push the north back out, right? So you need to remember that. It's going to be north. Why? To repel the magnet or push it out or whatever. So just two ways in which the deflection of the galvanometer can be reversed. Obviously, the easiest one is to probably push the south in first. Let's see. Let's check the marking scheme. I don't want to say anything that's wrong. So any two from move magnet to the right. Okay, and then insert the south. Okay, yeah, these are. Okay, yeah. So these both work. These are the easiest ones. Insert the south pole first, and insert the north pole. But remember, this is the coil. Our magnet's over here. They said insert the north pole, but from where? Insert it over here from the right. From the left, sorry. From the other end. So this is a very, very, very easy 2-mark question. These two will be the easiest ones. Obviously, moving the magnet out, like انت عندك الcoil, right? Moving the magnet, pushing it out, obviously will reverse the deflection, because when you pushed it in, the galvanometer is like this. So you're pushing it out, obviously the galvanometer is going to go back to the left, right? Like, okay. New past paper. Now May June 2018, again paper 4.2, كلهم paper 4.2. So question 9, it shows ABCD was a coil with 2 turns, and the coil is in a magnetic field. When there's a current in the coil, so بيحط current, obviously we're in a magnetic field, the coil experiences a turning effect, which is obvious. Why would it turn? Enter, you turn on the current in a magnetic field, you're going to start seeing turns. Why? Remember, I will with B will get you what? F, right? So obviously there's going to be a turning effect due to the presence of 2 forces acting vertically opposite to each other. Let's see. I want to show you the marking scheme. Many people here would say due to the presence of a couple of moments, or a couple, right? A couple forces, which I guess would be correct, but the way they worded it here in the marking scheme was forces on A, B, and C, D in opposite directions, which is obviously not wrong. Like, it's the same thing. But I don't know, the first thing I thought was, there's moment. That's the thing. That's the way they taught us in the class. But The thing is with Cambridge, they want you to get straight to the point. Okay, moments. I don't care about moment. What are the forces? Okay, so there's probably going to be a force going like this and a force going like this, which is going to cause a turning effect, right? Okay, part II. The value of the current is 3 ampere. Place one tick in each column of the table to indicate how the turning effect changes with the change described. So, turning effect decreased by factor 4. What? Oh, wait, I get the question. I thought it's each one here gets an answer here, like this. No, no, no. So, over here, this one would be which one here? You know what I mean? Because it's a 3 mark question. That makes way more sense. So, number of turns on coil is increased to 6. So, how many turns over here? We have 2 turns. So, if you're multiplying the number of turns by 3, what's going to happen to the turning effect? Obviously, it's going to increase by a factor of 3, right? Because they're directly proportional to each other. Now, the current is 3 amperes. It's increased to 9 ampere. So, again, we multiplied it by 3. So, the turning effect should also increase by a factor of 3. Then we said that the strength of the magnetic field is decreased by a factor of 2. So what should happen to the turning effect? It should also decrease by a factor of 2. They're directly proportional to each other. So let's double check the marking scheme over here. So increased by factor 3, increased by factor 3, decreased by factor of 2. There you go. Question, okay, part B. Figure 9.2 shows a magnet held just below a vertical coil connected to a galvanometer. The magnet is released. State any effect on the galvanometer. Obviously, there should be a deflection, right? Because you had over here a magnet inserted. You release it. There's a force inside a current. Sorry. You have a force inside the magnetic field over here, which is going to cause a deflection on the galvanometer. So FBI, why is it going to cause a deflection? Because you have a force, it's falling down, that's a force. It's inside a magnetic field, which is going to cause the induced current. Always, induced currents are very, very small. That's why we always have the same experiment you're seeing in every past paper. Galvanometer. So let's see part B. What is the effect? It deflects, and did they say explain? What did they say? State any effect. It's 2 marks. So it's going to deflect, and it should, obviously, return to 0. When you release, over here we're removing the magnet outside. So let me draw for you 2 cases. So you have over here a galvanometer. Over here you have your coil, right? And you insert a magnet over here, north, south. I'm going to change this. And this is over here, the galvanometer. It's obviously going to deflect, right? This is when the magnet is inside. But when the magnet is outside, over here, galvanometer, this is the galvanometer, and خلاص, you took the magnet, خلاص, it's over here now. You took it out. Obviously, it's going to return back to where? Back to, I think it's like this, back to 0. Right? Because it's like this 0, 10, 20, 30, 40, and so on and so forth. Right? So it's going to return back to 0. But over here, it's at 50. So since it's 2 marks, it's not sufficient to just say it deflects. Right? It deflects, and what happens since you're removing it, you're releasing it out, and returns to 0. State any effect on the magnetic field produced by the coil. Always with this experiment of magnetic field and what pole is it with the coil, this experiment, like I told you, there's always going to be 2 questions. One question about the induced current and one question about the induced magnetic field. What is the induced magnetic field? Remember, the induced current comes from Faraday's law. Induced change in magnetic flux, that's your induced current. Lenz's law said, okay, this induced current, it's going to oppose and cause a magnetic field that opposes the motion of your magnet, right? So since now you're releasing it, what's going to be the magnetic field? It's going to want to pull it back up, right? So state any effect on the magnetic field produced by the coil. What's the magnetic field of the coil going to be? It's going to be pulling it back up, so it's going to attract. It will attract. Let's say it will act as what? Always state the polarity. Since it's 2 marks, if you just say it's going to push it back up, pull it back up, it's going to be wrong. You need to say extra stuff. That's the thing with IGCSE. Always check how many marks, and according to how many marks, write as much as you can. This is north, so to pull it back up, it will act as a south pole and attract the magnet. Let's check our answer key. It produces a magnetic field, yeah, uh, S pole at bottom. Okay, hold up. I think if you say this, you should get 2 marks. But they're saying they're counting the first mark, 1 mark for saying that it produces a magnetic field. I guess, yani, from what I'm saying here, it means I produced a magnetic field, obviously. So, to be on the safe side, if you see a question like this, state any effect on the magnetic field, say, obviously it's changing, right? It's changing. Why is it changing? Because when it was inside, it was repelling, but now when it's falling down, it's changing. So you can say the magnetic field, I'm just gonna say B, the magnetic field changes, and now it will act as a south pole and attract the magnet. New past paper, May June 2019, again paper 4.2. Describe how to demagnetize a power magnet using alternating current in a coil. Okay, and it's 3 marks. Okay, 3 marks. So I don't expect many of you to know this because, and I honestly I didn't know it. I just read it now for the first time. But I don't think it was in our book. But you can demagnetize magnets. We know by blasting it with electric charge. But here they're saying alternating current. So you can't just say plug it in and then just put too much current and it's just gonna. No, that won't work. To demagnetize a magnet, you want to make it in a way that it doesn't have any current flowing through it. You want to reduce the current in it to 0, because when there's 0 current, the magnet won't work. So I'm going to show you the marking scheme, and I'll kind of translate what they're trying to say. So obviously the first mark is place the magnet in the coil, right? In the coil, the alternating current coil. So that's your first mark. Then they said either this process or this process. The first process talks about, okay, you place the magnet in the coil, slowly take out the magnet while the coil is switched on. This way, because alternating currents look like this, right? So if you're gradually taking it out, the alternating current is constantly switching current. So the magnet is going to be like, خلاص, man, I'm not in the mood for this. خلاص, I don't want to be a magnet anymore. It just goes out, and as you're pulling it, it just loses its ability to become a magnet. So that's the first one, and that's why the first one kind of works. The second one is just reduce the current to 0. So we plug it in, reduce the current to 0. You have this over here, right? And then after you plug it in, go take this alternating coil and take it down. Take the current to 0. This way, خلاص, you're like forcing the magnet to have 0 current inside of it. Honestly, they both make sense. If I were in an exam, I would just I would write any. It doesn't matter. So the first thing you'd say is place the magnet, plug it into the coil. Then you say slowly take the magnet out while the coil is switched on. This is very important. What's easier is just write this one, because this one you have to say while the coil is switched on. Some people might forget to write that. So plug it into the coil and then reduce the current of the alternating current to 0. Very, very easy. Question part B. Figure 9.1 shows a DC motor. Explain the purpose of the split ring commutator. This one over here. So this is the DC motor. This is the split ring commutator. Obviously, the split ring commutator makes sure that the polarity is the same. So make sure that the direction of motion is the same, so that the coil keeps on moving in the same direction, right? And how does it do that? It does it by, let's say the positive side is the negative side. It does it by switching polarities every half a rotation. So it's a 3-mark question, so I don't want to say stuff that might confuse you. So I'm just going to open up the marking scheme and show you. Obviously, the first one is or with what? Hold on. Okay, this means or words to that effect. So basically, you can say this in whatever way you want, but whenever you see an underlined word, that means you have to say that word. So the first thing obviously you're going to say is it keeps the coil rotating in the same direction. And I would have said it in the same words. How does it do it? It does it by changing the polarity or direction of current. That doesn't matter every half rotation. So actually, what I said earlier was correct. I wouldn't say by changing direction of current, and the first thing I'd say is by changing. Well, obviously, change direction of current. I'd say by changing the polarity of the wire or the current. خلاص, this is nice. First mark is keeps the coil rotating in the same direction. Second mark, it does it by changing the direction of the current every what? Every half a rotation. You could say every half cycle, every half rotation, whatever. Uh, Here, the voltage of the power supply is increased. State the effect this has on the motor. Obviously, increase the voltage, increase the power. There's more current flowing. What's gonna happen? Obviously, it's gonna rotate faster. It's not that hard. So over here you have a DC motor, and they said explain the direction of rotation. If they didn't give you the polarity, then there's no way you can do it. Okay? So they gave you this is the positive side and this is the negative side, right? That means current flows from positive to negative. So if you want to write it like this, you're gonna have to draw the current like this, right? Over here, like this. Obviously too many arrows. I'm not gonna draw this many arrows in my exam. What I care about over here is this. Okay, over here on the motor. This goes like this goes like this. We know that the magnetic field goes from north to south, so it's gonna be like this, right? Type. You know that the direction of the rotation comes from two forces. Either this is going up, this is going down, which causes a clockwise rotation, or either this is going down, this is going up, which is anti-clockwise. You need to figure that out. Which one's which? Okay, they're saying as seen from point X. And I don't care what point X is, I don't care. But to solve, I need to know the direction of the forces. How are you going to do this? You have your current, direction of current, you have the magnetic field. You want to know the direction of the force. So we're going to use the IBF rule, right? Many people do it another way. I can't turn on my camera right now because I'm on my tablet. But I'm going to try and draw the rule for you. So you have three fingers. Your thumb is I, your index is B, and then wherever direction your middle finger will point, that is the force. So I'm gonna start. The current is going this way, right? It's going, you can say, out, right? So you can point your thumb outwards, right? And then the magnetic field is going to the right. So you take your index finger and you point it to the right. Now extend your middle finger and it's going to be pointing up if you extend it. Okay, so that means over here the force is going to be up, and if this is up, this is going to be down, the one on the right. But you could say like you need to actually write it. By the way, in your exam, most of the time they will give you marks for these arrows. Okay, even though it's not required, but it will count as a mark if you don't explain it over here, but you have the arrow present, and in this case that counts. If you don't explain, you could just say see arrows on diagram. That would be correct, عادي. Anyway, on the right side now, you have now your thumb for current pointing inwards, right? Again, your magnetic field pointing to the right. Extend your middle finger. Where is it going to go? It's going to go down, right? So that means your force is going to be down. So what does that mean? You're going to go clockwise, right? So over here at X, what's the direction going to be? Clockwise. Y, the force on the left is up, force on right is down, right? That's correct. In this case, if you just said see arrows on diagram, that's correct. But don't rely on it, obviously. If you want the marks, you should write this over here, okay? The coil rotates through 90 degrees from the position shown. State what happens to the moment in this position. So now it's like this. It rotates 90 degrees, so that way the coil is kind of like, how can I say, it's kind of like, hold up. Over here, you should know that when the face is perpendicular, when the coil is perpendicular, to the magnetic field, there's going to be zero moment, right? There's going to be zero moment. How can you confirm this as well? There's going to be no more current when it's perpendicular. Why? Because over here, you see this, it's going to lose contact with the brush, with the split ring commutator. Over here, when it rotates, خلاص, the wires are going to be in contact with this gap, okay, when it rotates 90 degrees. So you could say there's going to be, what's going to happen to the moment? Zero. That's it. Okay, you can see over here, zero moment. هلا question. Okay, part I. The coil is rotated 380 degrees from the position shown. By considering the forces on the coil, explain how the split ring commutator enables the motor to turn continuously. This is like the one we had previously. Rotated 180 degrees, so command now it's upside down, right? How does it do this? It allows, what does it do when it splits 180 degrees? You guys know it changes the polarity and it changes the direction of the current, not the rotation. I'm saying about the direction of the current. It changes every half rotation. Every half rotation, yani every 180 degrees. Because into when you flip this upside down, the direction of the current, you have to change it to ensure that the rotation keeps on going in the same direction. If you don't, it's going to rotate backwards and you're going to be back to your starting position. So how does it enable it to run continuously? It changes the direction of the current, which ensures the forces are still in the same direction. Let's see here what they said. It changes the direction in the current, so the forces will still be up on the left and down on the right. Same thing that I said. Question 7, this is our last one. May, June 2022, paper 4.2. Okay, this is very easy. They gave you the compass, it's in between A and B, which is a magnet. They're asking us to find what's the polarity of A, what's the polarity of B, and which one's north, which one's south. You should know that the compass doesn't point in the direction of the North Pole, it points in the direction of the magnetic field. So the north of the compass always points in the direction of the magnetic field. And you guys know that the magnetic field goes from north to south. So if you have a magnet like this, north south, this is how the magnetic field will go, right? These are the flux patterns. And this is by the way why actually the North Pole is actually south and the South Pole is actually the magnetic north. That's why actually. So when the compass points north, that's just the direction of the magnetic field. And you guys know the direction of the magnetic field goes from north to south. So that's why A is north, B is south. Okay? So that's actually a fun fact you should know. You should actually know this. That the compass doesn't point in the north, it points in the direction of the force that the north produces. And that, in other words, is it points in the direction of the magnetic field, it goes from north to south. 7.2 part B shows a wire placed between two poles carrying a current in the direction of the arrow. This is the current going to the right. On figure 7.2, draw an arrow to show the direction of the force on the wire due to the magnetic field. So obviously, you have the current going like this, I. You have the magnetic field going like this, B. So where's the force going to be? We're going to try with our finger. So your thumb is I. Yeah, if I was saying, for I is going to be to the right, since obviously they showed us the current going to the right. You have B going over here inwards, because north to south, right? North to south. So this is B. Release your middle finger, it's going to be going upwards now. So this is going to be the force. So draw an arrow to show the direction of the force. It should just be an arrow going vertically upwards. And you can label it by F. Okay. So for this part over here, part C, I was a bit confused, but now I get it. They're saying beta particle. Okay, beta particles are like electrons. Remember our rule here, they're giving us the direction of the flow of electrons. Okay, I, B, F. Current, induced electric current, not flow of electrons. You know that the flow of electrons is the opposite direction of the current. So if they're giving us the flow of electrons to the right, that means I'm going to draw an arrow to the left and I'm going to label this as I. Okay, and now when I use my IVF rule, thumb going to the left, obviously the magnetic field is going from north to south, so it's going to be going like this, right? So we're going to call this B. Extend your middle finger, it's going to go down, right? Extended is going to go down. So that means the arrow of the force is going to be going like this. We're going to label this F. Like this, we're done. Thank you so much for watching, and good luck in your periodic.